Welcome back, students. In the last video we talked about the origin of resistivity. We talked about drift velocity, and then we established a relationship between current in a conductor and the drift velocity. The simplest thing that we used to remember that equation was I is equal to Vana. V is actually Vd, the drift velocity, and then E is the electric charge on the electron. It's 1.6 × 10⁻³ - 19 coulomb. And then N is the number of free electrons per unit volume of the conductor, the material. It is specific to a material. If it is copper, then you will have one N value, and if it is iron, you will have a different N value. And if it is silver, you will have yet another N value. And then A is the cross-sectional area of the conductor. So I is equal to Vana was the equation we derived yesterday. So there was this drift velocity, and there was another term, relaxation time, which is actually the time between collisions, the average time between collisions of free electron in the conductor. So relaxation time and drift velocity were the two things that we talked about in the previous video. And using them, we established a relationship between I, the current flowing through the conductor, and the drift velocity. And in that process, we also derived the equation for resistivity. Rho was equal to m by neat, m being the mass of the electron, and n again is the number of free electrons per unit volume of the conducting material, and E is the electronic charge, and then tau is the relaxation time. And conductivity was the reciprocal of resistivity, so conductivity would have been neat by m. Okay, so these are things that we did in the previous video. Okay. In this video, let's talk about another important quantity, which is mobility. Okay. Mobility of an electron is defined as the drift velocity per unit field, E. So mobility of an electron, mu, is defined to be Vd, the drift velocity. In this case, like, we'll just take the speed. You won't take the direction, so you just take the speed. So I will have the magnitude. Okay, drift velocity divided by E. So per unit field, if E is per unit field, what would be the drift velocity of the electron? So clearly the drift velocity will change if E is changing. E is dependent on the voltage that you maintain, right? So if the voltage increases, then the current will increase, as you know. And if the current increases, then the drift velocity should increase, because we know that I is equal to VE and A. So A is a cross-sectional area of the conductor, so that's not going to change. And N is the number of free electrons per unit volume of the conducting material, that will not change. E is a charge on the electron, that will also not change. So the only thing that can change is the drift velocity Vd when current changes in the conductor. So as you increase the potential across the conductor, suppose we have the conductor here, and if you increase the potential across the conductor, then I through this will increase. If I increases, Vd increases. But then if increase V, the potential, then E inside the conductor is also increasing. Okay, this also increases with V. So one important measure is this mobility, which is Vd per unit field. Okay, so this is called as mobility electron. So mu is called as the mobility. Electron mobility. So this is another important idea. There would be problems involving this quantity also. So what we'll do now is, now that we've discussed a lot of ideas, the drift velocity, and then the relationship between current and drift velocity, and the resistivity, and also mobility, and all this. Let's start doing some example problems, and then continue with the lesson after that. The example problem that I'm going to do first is this. Example 3.1. Example 3.1. Let me read the problem first. It has two parts. The first part A is this. Estimate the average drift speed of conduction electrons in a copper wire of cross-sectional area 1.0 into 10 to the power minus 7 meters squared, carrying a current of 1.5 amperes. Assume that each copper atom contributes roughly 1 electron for conduction. The density of copper is 9 into 10 to the power 3 kilogram per meter cube, and its atomic mass is 63.5 atomic mass units. So that's the first part. So the first part, they want you to find the drift speed of the conduction electron in a copper wire whose cross section is given, and the current through the wire is also given. Okay, and then there are some other numbers given. So let's see like why they've been given. Basically, the first thing is, the first part of the question is for you to find the drift velocity of the electron, the conduction electron in that copper wire. And the second part is this. Compare the drift speed obtained above with 1. Thermal speeds of copper atoms at ordinary temperature. 2. Speed of propagation of electric field along the conductor which causes the drift motion. So that's the second part. First, let's do the first part. Okay. So what is the first part? They want you to find the average drift speed of conduction electrons in a copper wire of cross-sectional area 1.0 into 10 to the power minus 7 meters squared, carrying a current of 1.5 amperes. So what you need to find is drift speed. That is A. Okay. So what do you know? You know that I is equal to N. V, E, N, A. This is drift speed. A is given, the cross-sectional area. A is given to be 1.0 into 10 to the power minus 7 meters squared. 1.0 into 10 to the power minus 7 meters squared. Okay. I is given, I is equal to 1.5 ampere. E value you know anyway, E is equal to 1.6 into 10 to the power minus 90 coulomb. But what you don't know is this N, the number of free electrons in the copper wire or in copper in general. Okay. It's for the material. Okay. How do you do that? So far. Well, they have given you something else. What have they given? They said that copper contributes 1 free electron per atom. So 1 free electron per atom. Okay. Next. They have given you the density of copper. So rho, in this case is density, mass density is equal to 9 into 10 power 3 kilogram per meter cube. So that's the density of copper. And then the atomic mass unit is also given. The atomic mass unit, atomic mass of copper, I'll call it as okay. This is let's say this is A, that is equal to, no, this is confused. So mass of atomic mass of copper. I'll just put it this way. Okay? It is a different symbol, but I'll just use that. That is given as 63.5 atomic mass units. So now you need to find the number of electrons in 1 meter cube of atom. So that is N. N is the number of free electrons in 1 meter cube of copper. We know that 1 electron is contributed per atom. So you need to find out how many electrons are going to be in 1 meter cube of copper. Okay. Well, this is given. What is this? This is the density, mass density of copper. It's not resistivity, it's mass density of copper. So that's a problem with physics. You know, there are only a few symbols and there are many quantities, and then you end up using the same symbol for multiple quantities by thereby confusing people. But here, this is mass density. I mean, to make matters easier, I'll say this is rho m. This is different from resistivity. Okay? So this rho m is equal to mass per volume. Okay, so this is given as how much? 9 into 10 power 3 kilogram per meter cube. So if I take 1 meter cube of volume, then I'm going to have 9 into 10 power 3 kilogram of copper. So mass of copper per 1 meter cube of copper is 9 into 10 power 3 kilogram. Okay. So for unit volume, the mass of copper is actually equal to rho m into V, that's equal to 1. So 9 into 10 power 3, where V is equal to 1 kilograms. Okay. So if I take 1 meter cube of copper, that's going to weigh 9 tons. That's as simple as that. Now I need to find out how many atoms are in 9 tons of copper. And I know, if I know the number of atoms in 9 tons of copper, then I know the number of free electrons in 9 tons of copper. How? Because I know each atom contributes 1 electron. So if I calculate the number of atoms, then that will be equal to the number of free electrons in 1 meter cube of copper. Okay? Then how do we do it? Well, what do we know? I know this. What do we know? I know because the atomic mass unit is 63.5 for copper. I know the Avogadro number of copper atoms will weigh 63.5 grams. So I know that's in 63.5 grams, and I'm going to have 6.022 into 10 power 23 atoms. Okay, so which means how much would I have in 1 kilogram basically? So I can convert that into kilograms, right? So that's going to be 63.5 into 10 power minus 3 kg is equal to 6.022 into 10 power 23 atoms. So in 1 kg, I'll have 6.022 into 10 power 23 by 63.5 into 10 power minus 3 atoms in 1 kg. But what is the mass in 1 meter cube of copper? The mass is 9 into 10 power 3 kg. So how many atoms are going to be there in 9 into 10 power 3 kg of copper? So that would be in 9 into 10 power 3 kg of copper, I'm going to have 6.022 into 10 power 23 by 63.5 to 10 power minus 3 into 9 into 10 power 3 atoms. That's what I'm going to have. Well, if I do certain manipulations, okay, if we calculate this number, this is like somewhere around 9, it is 63.5, it is like 7, 1 by 70 or something, 9, 1 by 70, so that becomes 7 into 10 power minus 2, then 6 by 7, and then 10 power minus 2 can go, and that will become 1023 plus 3 to 26, and then this minus 2, 28, and that 6 by 7 would be approximately 8.5, I suppose. Here. The answer is actually, if you do this 8.5 into 10 power 28 atoms. So in 9 into 10 power 3 kg, in 9 tons of copper, we are going to have 8.5 into 10 power 28 atoms of copper. And each copper atom will contribute 1 free electron. So the number of free electrons in 1 meter cube of copper is going to be 8.5 into 10 power 28. Okay, so this n value, the number of electrons per unit volume, n is equal to 8.5 into 10 power 28. So this is the same free electrons, n is equal to same 8.5 into 10 power 28 electrons. That's atoms, 1 electron per atom, so there are so many free electrons in 1 meter cube. So that's the number we're going to use here. Okay, so it's so many electrons per meter cube of copper. So I can use this and find this number, Vd, right? So what is I? I is 1.5 is equal to Vd, which I don't know. E is 1.6 to 10 power minus 19, and then n is 8.5 into 10 power 28, and then A is 1 into 10 power minus 7. So this gives you it's 10 power minus 7, 1926. So this cancel 10 power 2 is what you will get here. So Vd into 1.6 into 8.5 into 10 power, this is 26, 28, so 10 power 2. Okay. So this is what you are going to get. So what is Vd? Vd is equal to 1.5 by 1.6 into 8.5 10 power 2. Okay. So what can happen here? So 1.5, 1.6 roughly it will cancel, right? Roughly the same. So it's effectively it's 1 by 8.5. That would be like 1 by 9. So you get 1.11. So it is roughly 0.11 by 10 power 2. So if I take this up, then that's going to have 1.1 into 10 power minus 3 meter per second. Okay. So that is equal to 1.1 millimeter per second. So Vd. So note that when 1.5 amperes of current is flowing through a copper wire of area 1 into 10 power minus 7 meters squared, then the drift velocity of the electrons from one end to the other end is very, very, very low. The electrons kind of on the average move 1.1 millimeter per second. Very slow movement. Actually, it's not very slow per se, because you're taking only this direction. They'll go collide, then come back, and then again collide, then do this, and it's like they'll jostle their way out of the conductor. So it looked like they move very slowly in this direction. So 1.1 millimeter per second. You see, like if you take this, say 1 meter long tube light, and you see it's going to take roughly 1000 seconds to come out of the tube light from one end to the other end. An electron entering one end will take 1000 seconds to come out of the other end. So it's pretty long time, right? 60 seconds is 1 minute, and then 3600 seconds is actually 1 hour. So that is 1000 seconds would be about 15 minutes for it to go from one end to the other end. Okay, so 15 to 20 minutes is what it takes to go from one end to the other for one electron. So the drift velocity, the drift speed is very, very, very small. Okay, that's why you call it as drift. It is drifting, yeah, like a wooden log in water, in the ocean. It's kind of drift, right? Like it won't go fast. It will slowly move from one place to the other. So it is not a real. It's not traveling really fast. Just drifting slowly. So that's why you call it as drift velocity or drift speed. So small. Okay, so that is the first part of the lesson, the problem. What is the second part? The second part is this: compare the drift speed obtained above with thermal speeds of copper atoms at ordinary temperatures. Thermal speeds of copper atoms, ordinary temperatures. Well, in the 11th standard, in the kinetic theory of gases lesson, then you have come across this thing. Okay. So temperature is actually a measure of the kinetic energy of the molecules. Okay. So that's what you come across. So if we were to use that, so R from V square, which is the kinetic energy, is equal to 3 by 2, and then Boltzmann constant into temperature. So this is the expression you have. So temperature, this is in kelvins. Okay, you have Boltzmann constant. Okay, and then if you plug in all these numbers, what's generally like room temperature is how much? Roughly about 23 degrees centigrade or something. So it's in kelvins, it's about 300 Kelvin. So T is about 300 Kelvin. You have mentioned temperature in Kelvin. So you get the Boltzmann constant, then you get the mass of electron, then you should be able to find the velocity by using this expression. When you do that, you get this. At 300 Kelvin, which is about 27 degree Celsius, okay, room temperature, you are going to have a speed of V, if you calculate V, like this. So V can be calculated like this, right? You can cancel. V can be written as 3 kBt by mass of electrons square root. So if you plug in the numbers, you are going to get 2 into 10 power 2 meter per second. So the speed of electrons at this temperature, the room temperature, is about 200 meters per second. So in a second it will cross 200 meters. That is how fast they are moving in room temperature, in a conductor. In this conductor right now, these electrons are moving at 200 meters per second speed. But then if I'm going to connect this conductor to a voltage supply, and then if we allow 1.5 amperes of current to pass through it, then it is copper, and then it has the same area as this. Take a wire like that. If we do it, then the electron is going to have an additional drift velocity of 1.1 millimeter per second. So it will slowly drift to the other side. Okay. So the thermal speeds are in hundreds of meters, and the drift velocity in millimeters per second. So you can see the huge difference between these two things. Okay. So thermal velocity is much greater than the drift velocity caused by an electric field, a conductor. The second part is the speed of propagation of electric field along a conductor which causes a drift motion. Well, the speed of propagation of electric field, the moment you set this up, then the electric field will be set up. How fast will the electric field be set up? Well, the electric field is set up with the speed of light, 3 into 10 to the 8 meters per second. We'll study about all that later, okay? In the later lessons we'll study about this stuff. But then, you remember this point, that when I set up an electric field in a conductor, E is set up pretty quickly. I mean, because it's set up really fast with the speed of light, 3 into 10 to the 8 meters per second. So it is very, very, very fast. E is set up quickly. Then the thermal agitation of the electrons is hundreds of meters per second. But then the drift speed of the electron, because of the electric field they present there, it's very, very slow. It appears to be slow because they go hit and then come back and then hit something else. It's very jostling. It's like one tiny room full of lots of people, each of them trying to get out. So they go collide with each other, do this, do that, and finally people will come out. So it's not very easy for a person who is entering such a room to get out of the room very quickly. Okay, so that is exactly what is happening in this. It's not that the electrons are moving slowly; they're actually moving really fast inside. But then the time it takes to cross effectively a certain length of a conductor is pretty long for an electron, because it's going to get buffeted in all directions, and finally it's going to make its exit once it has made its entry. Okay, so it's the time it takes between entry into the conductor and exit out of the conductor is pretty long, even though inside they may be moving with hundreds of meters per second speed. So that is what we need to understand from this problem. Hope it's clear to you. Let's also do problem 3.2. Let me read out the problem. It's not a problem that you work out on the board, but it's a problem that requires explanations for the questions asked. Okay. Let me start with the first one. A. In example 3.1, the electron drift speed is estimated to be only a few millimeters per second for currents in the range of a few amperes. How then is current established almost the instant a circuit is closed? Okay. See, I hope you understand the question. If it takes so long, if the electrons move so slowly from one end of the conductor to the other end of the conductor, how come as soon as you set up an electric field, as soon as you connect a battery, then you start getting currents? You're not going to wait for 15 to 20 minutes for you to get the current out, right? Immediately you see the current coming out of it. How does it happen? See, to answer this, we need to understand this part. Well, the moment you connect the battery, as I said, the electric field is set up instantly, almost instantly, at the speed of light inside the conductor. So the electric field is present inside the conductor. And then electrons are also present everywhere in the conductor. So the electrons are present here at one end of the conductor, and the electrons are also present at the other end of the conductor and every other place in between. The free electrons I'm talking about. And there is E everywhere. So what happens is that there is E at the end of the conductor as there is at the beginning of the conductor, right? So the electrons there, and they will start moving out. Okay. So as soon as you connect the battery, E is set up everywhere. So first the electrons at the end will start moving out. Okay. And then the electrons at the beginning of the conductor, then they will start drifting slowly. So they keep going out, and as these electrons keep coming in, then other electrons will be coming from the battery and other places, and they just get in. So they get in and then they move slowly. So you have a continuous current from the very instant, or almost at the very instant you set up the voltage across the conductor, set up the field across the conductor. So when you connect a battery across a conductor, you set up the field inside the conductor, and that happens instantaneously, almost instantaneously. 3 into 10 to the power 8 meter per second is the speed at which E in a conductor is set up. So E is present everywhere in the conductor. So the electrons at the end of the conductor will leave. Electrons at the beginning of the conductor will start moving inside the conductor. So you get the current almost instantaneously. Okay, so that is the reason. So that is answering the first question. The second question is this. The electron drift arises due to the force experienced by electrons in the electric field inside the conductor. But force should cause acceleration. Why then do the electrons acquire a steady average drift speed? Well, E is inside. E is set up inside the field, inside the conductor. The field is set up inside the conductor, and there are electrons inside. So they're charged particles. They're going to experience a force as per Coulomb's law. That's what we've been discussing all along. So if a body is experiencing a force, then it must experience an acceleration. If it experiences an acceleration, then it should accelerate and its speed should change continuously. How come then these electrons acquire a small speed only? What happens then? Are they not getting accelerated? They must be getting accelerated, right? So what is happening then? Well, the answer is this. Yes, they get accelerated. The electrons inside, the free electrons inside the conductor are getting accelerated. But then what happens is they go collide, and then they come back, then lose their speed, right? Because the field, suppose the electrons are experiencing force in this direction. Okay? Then they move, then they go collide with the atom, then they start moving in this direction. Suppose there is head-on collision, okay? Then the electron will start moving back like this. But then the field is still trying to push it that way. So there is this braking effect that takes place as it bounces back. Then it stops. Then it again gets accelerated. Okay? So the angles are slightly different, and then it goes and hits, then it comes like this and then slows down, and then goes like that, comes down, slows like that, comes down. So on the average, you get an average speed. That is because the electron gathers speed, hits the atom, then it slows down to 0 or something. It loses all its energy that it's gained, and after that it gains the speed again, and that is the reason. Electrons in a conductor do not have a very high speed. Okay, they get both accelerated and decelerated because of the direction in which they move after collision. So that's the reason you don't see very high speeds for the drift velocity. So that is the explanation for question 2. Then part 3. If the electron drift speed is so small and the electron's charge is small, how can we still obtain large amounts of current in the conductor? Electronic charge is small, electron's drift speed is also small, then how can you how can you get very high values of current in a conductor? And as I told you, that there are lots and lots of electrons, free electrons inside a conductor. We saw that 8.5 into 10 to the power 28 electrons inside, like in 1 meter cube of copper. Okay, so there are lots and lots of free electrons. They are also in the beginning, and then they are distributed throughout the wire. So the moment you set up a field, and lots of electrons will move, even though they move slowly, then high number of electrons move. So that contributes a very high current. Even though the speed is small, the number of electrons, the charge is high, and that way you get very high current. Then D, fourth question. When electrons drift in a metal from lower to higher potential, Does it mean that all the free electrons of the metal are moving in the same direction? No, certainly not. All the free electrons are not moving in the same direction. If they collide, they come back, it's like there's lots of chaos that's happening inside the conductor. Not all the free electrons are moving in the same direction. Some will be moving in one direction, some will be moving in the other direction. So it is, the drift speed is the average speed. Okay. You need to understand that. And then E, or the paths of electrons straight lines between successive collisions with positive ions of the metal. Yeah, because the metal will have positive ions, right? Because they have lost one electron in the case of copper. In the sense, they're free to move everywhere. So the atom as a whole is not exactly neutral, because not all the electrons are with the atom. Some are wandering around. So the atom becomes positive ion. Okay? And there are free electrons there anyway. So that's what they mean. Or the paths of electrons straight lines between successive collisions in the absence of electric field and in the presence of electric field. Well, in the absence of electric field, there will be straight lines, because they will go, collide, then go back, they will do this stuff. Okay? But then the moment an electric field is set up, then it is no longer, it can no longer be a straight line unless the electron is moving in the direction of the field, or in the opposite direction of the field. Okay? So only then only then can go in a straight line. Otherwise it will be curved. It's like this, right? For example, if I take this pen and then if I throw it this way, then like which direction is the gravity acting? Down. Okay? But then the velocity is in this direction. Then what happens? It is not going in a straight line now. Now it's going to get curved. This will have projectile motion, right? In this case. So it will go and then the path is curved. So likewise, in the conductor also, because of the establishment of the electric field, the electrons will no longer move in a straight line, because there is an electrostatic force acting on the electron. And if the direction of motion is not aligned with the field, then the electron will move in curved paths. So that is the answer to question number 5. Hope all these explanations that I have given you make sense to you. If not, please let me know. With these 2 example problems, I want to finish this video session, because I need to start a new topic, and it's also a big topic. I don't want to do it now. Okay? I want to do it continuously, probably in the next video. So this kind of concludes the first part of the lesson, where we talk about current, electricity. We have made a transition from electrostatics to electrodynamics, where current is involved. Charges start moving. And we talked about how charges start moving. If you maintain the potential difference between 2 ends of a conductor, then the field will be set up inside the conductor, and then that field will drive these electrons, the charges inside the conductor. So that is how the current flows in a conductor, and that's what we started the lesson with. And after that we talked about what happens inside the conductor. We talked about the thermal velocity, the velocity of the electrons due to thermal agitation, and also the drift velocity, which is due to this E, the electric field that you set up inside the conductor. And then we related that to resistivity of the conductor. So that derivation is a very important derivation. It has been asked many times before. So go through the derivation and understand the derivation. It will be very useful to you. And if you understand the derivation really well, then you can answer lots of questions. So it's a very important derivation. So you have to really know the derivation. Okay? And then we also done a couple of problems to illustrate with numbers the exact scenario that happens inside a conductor. With those problems, we told you that the drift velocity is a very small speed. It's only in millimeters per second, whereas the thermal speed, the velocity due to thermal agitation, even at room temperatures, is in hundreds of meters per second. Okay? So we showed that to you through that example problem, and then we answered a few questions that might arise because of this difference. And how do you immediately get the current? If the electrons are moving so slowly inside the conductor, how do you immediately get the current in a conductor when you set up the electric field inside by connecting a battery? So we said that it's because lots and lots of electrons are there, free electrons are there in a conductor, and there are free electrons in the beginning and also in the end of the conductor, as they are in the middle of the conductor, every other place of the conductor. So when you set up the field is everywhere, so it is there at the end of the conductor also. Then it will start pushing the electrons which are at the end of the conductor out, and the other electrons will start moving slowly. And since there are lots and lots of electrons, then the desired current can be obtained. Even though the electrons move slowly, because of the sheer number, the charge is so much, even though the speed is so small. So you can get the desired current in the conductor. So this is what we have seen so far in this video. And we also have talked about electron mobility. Okay, that is the drift velocity per unit electric field. Okay. And that is also a very important idea. We have not done anything with it yet. We have not done any problem with it yet. But keep it in mind that we will be doing problems later with electron mobility. Okay. So with that, this session comes to an end, and then we'll start a new topic on resistance in the next video.